My name is Benjamin Thompson, and tonight I'll be going through Recitation Worksheet 24. So the general idea of this worksheet is that we'll go through the Lokta-Volterra model and examine some limitations of it, and then figure out ways in which to overcome those limitations. So the first part of the question is just identifying these limitations. So let's begin here. In part A, we're asked to look at the equation that describes the change in prey. If there are no predators, how will the prey population grow? Is this realistic? So we can say if the predators are 0, which means there's no predators, then the change equation for n simplifies to n prime is equal to bn. And recall that the solutions to this is the equation given by f of n is equal to e to the power of bn. A quick calculation shows that the derivative of that satisfies the change equation. And so if there are no predators, the population will grow in an exponential way. That is, we can say if there are no predators, there is exponential growth. Okay then. How about part B? What could we replace this term by to have something more realistic? So the reason why the exponential growth is unrealistic is, of course, exponential growth can't happen for all the time. Eventually, there will not be enough resources to support the population. And so we then need something that takes this into account, that is, has a crowding term. And logistic growth is a solid example of this. So for part C, we need to focus on the term which corresponds to a predator encountering and eating a prey. What term is that? This is just going to be the terms in which both P and N are mixed, and there's only one of those, which is this term up here. So we can just say this is the negative AN term, negative ANP. How about part D? Suppose we fix a specific amount of predators, for instance p is equal to 10. What happens to the term you have just written when n becomes larger and larger? So we can say that let's just use this number in the example. When p is equal to 10, the term simplifies and this is just going to simplify to 10a times n. And this term is just going to grow, linearly with n. So the larger n gets, the smaller the term gets. Okay, how about part E? In summary, what are the two limitations? At least the limitations that we've discussed so far. The first was that the exponential growth was, or is, unrealistic. And what was the second one? The second one was that the term which corresponds to the prey getting eaten can grow sort of arbitrarily large. And since this term is proportional to the number of predators, this essentially means that the amount that the predators can eat can grow arbitrarily large. And this is not a realistic assumption. What's the best way of saying this? Or what's a good way of saying this? All right, let's move on to part 2. And so now we start trying to change aspects of this model to improve upon the limitations. So we're asked in this part what function from one of the previous homeworks fits the description of something that starts at 0, increases and then levels off. This is just a sigmoid function. How about part B? Part B is asking what value of n should we choose for our sigmoid function given that the prey consumption grows quickly to begin with. We can follow the link given in the recitation worksheet to the Desmos graph online, which is given by this set here. And so we can see that this third column here is varying n. When n is very high, we can see that the initial increase is extremely flat, and the lower we get from n, the steeper it becomes. And so already choosing something like n equals 3 is too large, and which leaves us with n equals 1 and n equals 2. But really the one which gives us the fastest increase to begin with is n equals 1. So that's the one that we'll go with. Part C, we make a small change to this function and replace the 1 in the denominator by a parameter d. So let's just write out what our sigmoid function is. So normally we consider it to be this one, but now we're replacing the 1 with, I'll call this f tilde, with a d. And actually, since we already know that n is equal to 1, I think I should just go ahead and replace that immediately. And then we're asked, where does this name come from? The name being the half saturation density for D. The question gives us a hint. It says, just look at the value of the function when x is equal to D. I'm not sure why I put in f of D there, because when we actually evaluate it at f is equal to D, we just end up with 1/2. And so then that's where the name comes from. D is the value at which this sigmoid function is equal to 1/2. And if we're assuming this sigmoid function ranges between 0 and 1, I mean, of course, you can multiply it by a constant to scale it between 0 and whatever number you want. But in the simple case that it's just 0 and 1, then if this physically is representing some density, D, evaluating this at D is going to give us the density, the point at which the density is 1/2. Okay, part D. So using this function, write the new term for predator eats a prey. Let's recall what the previous term for predator eats a prey was. So the old term was negative an times p. And so the reason why this was flawed was that as n could grow arbitrarily large, this essentially meant that the amount at which the predators could eat in a given span of time could grow arbitrarily large. And so the point of using the sigmoid function was to replace the parameter n here with something that is more realistic. And so we simply want to replace the n in the old term with our new function. So this will then be negative a times x over d plus x. I mean, technically speaking, it's not an x because x here is actually representing the number of prey. So we really want n over d plus n times p. I suppose you could simplify this and write it as a fraction like this if you wanted to. Okay, part E. Now we need to write down the equation, the overall, the new version of the prey change equation, assuming that the growth is now going to be logistic growth instead. So logistic growth is just the birth rate times n, and then 1 minus n on k, where k is the carrying capacity. And now we need to subtract from this the amount of prey which is getting eaten, which, as we just determined, is given by this. Now let's consider the predator equation and how we can modify that. In part A, we're just asked to write down the normal logistic growth equation for population P with birth rate R2 and carrying capacity K. And then in part B, we are asked to determine the values for which the population P is increasing and decreasing. And so P is going to be increasing when P prime is, just think now, if you're watching this video, if P prime is going to be less than or greater than 0. Which one do we want? So P is going to be increasing when P prime is greater than 0, and P will be decreasing when P prime is less than 0. And so now we can just determine algebraically from the equation above the values at which P prime is going to be greater than 0 or less than 0. And so note that if we construct a table, so note that the change equation, or at least the right-hand side of the change equation, is a product of essentially two terms. We've got a P, and then we've got 1 minus P on K. If we then determine the ranges for which these values are positive or negative, we can then multiply those together to give us the overall ranges. So we're only considering here cases where p is greater than 0. And so let's see. Actually, it's probably best. I realize I'm probably getting a bit unnecessarily complicated here. So just note that since p is an animal population, it's always going to be positive. So we really don't need to consider that aspect. The only aspect of the right-hand side, which is going to determine if p prime is positive or negative, is sort of the part in the brackets over here. And so if this part here is positive, it means that this part here is less than 1. The only time this part here is going to be less than 1, though, is when the numerator is smaller than the denominator. And so that's just going to correspond to the time where p is less than k. And likewise, the option where p prime is greater than 0 is going to correspond to when p is greater than k. And let's just think, from a biological standpoint, does this make sense? This is somewhat of a circular question because there is a reason this constant k is called the carrying capacity. This is precisely because when the population is greater than k, the population is then going to decrease, or is going to be decreasing. And similarly, if the population is below it, then it's going to climb towards it. At least in all of these one variable systems. We have, of course, seen in the course many examples where if you have multiple species interacting, then you don't just have populations increasing or decreasing based on a single value. Okay, part C. If J preys are needed to support one predator, how many preys are needed to support a population of P? This is just a product of the two terms. Part D. If the number n of preys is smaller than your previous answer, what should happen to the predator population? Should it increase or decrease? Likewise, what happens if n is larger? So we can say that if n is less than jp, then I guess from a biological point of view, if there's a smaller number of preys than is needed to support the predators are going to start starving, and so some of them will die. That is to say, the predators will decrease. Predators will decrease. That's not super precise. We can say the predator population will decrease. And similarly, if n is greater than jp, then there's extra food around. Presumably this means that if new predators are born, then those new animals will live on. There'll be enough food to sustain them. That is, the predator population will increase. Part E. Use everything we've done before to determine what the carrying capacity of J predators is, and write the logistic equation for P prime. So the carrying capacity for J predators is just going to be exactly what we worked out in part D, right? It's going to be J times P. Actually, I think we're going to need to multiply this by a constant. since the j in part E is different to the j in part C. In part C, j was the number of preys needed to support one predator, whereas in part E we're saying j predators. Part of me wants to sort of modify this question a bit. So why don't we then say what's the carrying capacity of p predators? Then we can just say this will be equal to j times p, where j is the constant as in part C. And now everything's more consistent. Okay. Now we need to write the logistic equation for p prime. This will just be the one that we wrote above, but now we're replacing k with j times p. So yeah, so now we need to just put everything together. Or I should say just copy everything, since we've already worked out what the change equation for n prime was. Let's just copy this instead of me rewriting it out again. And then we'll paste the other one. Yeah. So yeah, I hope you found this video useful. And as always, if you have any additional questions, please come to office hours or post a question in Piazza. Best of luck on the quiz tomorrow.